Maths educational video, the chain rule. In this video, we are going to learn the chain rule for functions of two or more variables. But first, let's recall the chain rule in the one variable setting. If y is a function of x and x is a function of t, and assuming all functions are differentiable, the chain rule says dy dt is the product of dy dx and dx dt. This tree diagram gives you the relationship among the three variables. Arrows means depends on. So y depends on x and x depends on t. And along each arrow, we have the derivative connecting the two variables concerned. And the chain rule says dy dt is the product of the derivatives along the branch. Obviously, we can generalize the chain rule to the case when we have two or more variables. So here, back to our setting, we have z, a function of x and y. And both x and y are functions of a new variable t. In this case, we can draw a similar tree diagram, but this time with two branches, one for zxt and the other for zyt. And along each arrow, we have the derivative connecting the two variables concerned. And we're going to multiply the derivatives along each path. And what the chain rule tells us is we'll add the two outcomes. We can now extend the result to the case when z is a function of x and y, and x and y are in turn functions of two independent variables s and t. So in this case, we expect four branches: zxt, zxs, and zys, zyt. Total of four branches. Along each branch, we have a derivative, which is one connecting the two variables. And obviously, there are two derivatives of interest here. Either z versus s or z versus t. Because now z is also a function of two new independent variables s and t, we are going to use the partial derivative notation. Let's do them separately. First, we consider dz ds. We're going to use the chain rule in the same way, but this time we have to look at the correct paths or branches. We'll look at those connecting z and s, ignoring the one connecting z and t. So the branches involved are those in red. And along each branch, we multiply the derivatives concerned. So dz dx dx ds is the first term, dz dy and dy ds the second term. We do the same for dz dt. This time we will take those paths connecting z and t, indicated in red. Let's look at two examples. The first example illustrates the first version of the chain rule for functions of two variables. Here we have z a function of x and y are both functions of t. We are asked to find dz dt when t equals to 0. So we'll begin by finding dz dt in terms of x, y, and t. So this is the formula we've just seen, and our job is to find all the four terms on the right hand side. Those in red are derivatives of z with respect to x or y. But we have to replace them with expressions in t, because now z is a function of t. So x can be replaced with t cubed minus e power t, while y can be changed to e power t plus t. And now we are ready to evaluate the derivative when t equals to 0. And we can get the value of 10 quite easily, simply by substituting t equals 0 into the preceding expression. The next example shows the chain rule for the case when we have four branches. So W is a function of U and V, and U and V are both functions of S and T. We are first asked to find dW ds, so we take the correct branches. We look at all those paths connecting W and S. And we find all the derivatives required in this formula and simplify. Answer has to be in terms of the new variables S and T. We do likewise for dW dt, this time taking those paths connecting W and T. We end this video with a generalization of the chain rule. In this case, Z is a function of n variables x1 to xn. N can be anything from 2 onwards. And the x variables are all functions of m new independent variables, t1 to tm. And we can find the derivative of z versus t for any one of the m variables, t1 to tm. So for any k from 1 to m, dz dtk is given by this expression, and this can be found by taking the paths connecting z and tk. So this is the most general form of the chain rule.